Hello, everybody, and welcome to our special two-session webinar, What are the Odds? Producing Odds Ratios and Examining Interaction Effects Using Binary Logistic Regression. William Bannon of Stats Whisper bringing you the presentation. Now, binary logistic regression. It's an appropriate procedure whenever you're studying an outcome or dependent variable that has two categories. It could be yes, no, alive, dead, satisfied, not satisfied, any two categories. Now, the reason I wanted to do this webinar is this procedure offers tremendous benefits and is actually very straightforward and fairly easy to implement. So, the top benefit being that it produces the odds ratio effect size. The odds ratio effect size is an effect size that's immediately communicable to scientists and non-scientists alike. So if I say twice as likely, 3 times as likely, that's understandable to the general public as well as scientists. For example, if I said the Cohen's d was 0.5, right? Scientists might understand that, but not the general public, right? So we immediately have an immediately communicable effect size, and it also shows magnitude. We know 4 times more likely, right? 5 times more likely. So we're saying our magnitude is immediately recognizable too. So there are also a few test assumptions, right, relative to some other procedures, which we'll go over. So it's a fairly low maintenance statistical procedure, right? And also, as we said in the title, we'll be looking at interaction effects, which are very straightforward and recognizable using BLR, otherwise known as binary logistic regression. Okay, so here we are with our 7 steps of data analysis, which we'll go through. But first, let's orient ourselves to say, where does this BLR fall among these steps? Step 6, multivariate analysis. So binary logistic regression is a form of multivariate analysis. So obviously, we're going to have to do a few more steps before we get to the binary logistic regression, right? So these are the steps we'll cover in this webinar. We're first going to make our study map. We're going to map out what we're examining, right? So we need a sample study to illustrate how to use binary logistic regression. So it could be generalized and applied to your own study. Okay, we're going to skip data entry, go right to step 3, checks of data integrity, where we'll compare those test assumptions that we mentioned. Then we'll do the 3 phases of data analysis. Step 4, univariate analysis. Step 5, bivariate analysis. And then finally, step 6, the multivariate analysis with the full binary logistic regression model. And then in terms of step 7, the write-up and report, we'll have a sample writing, right, to look at. All right. So for our study here, our sample study, our vehicle for learning, right, we're going to look at our study map. So we're talking about quitting smoking. Specifically, if somebody goes through an intervention program, say we have 100 people, 50 go through an intervention program and 50 don't, right? Well, the 50 that went through the intervention program, will they be more likely not to start smoking again at the end of 1 year? Very interesting. Okay, so the research question formally stated, will attendees in an intervention program be more likely to have quit smoking for 1 year relative to those who did not attend the program? The hypothesis, of course, is that the intervention program attendees will be more likely to have quit smoking for 1 year relative to the non-attendees. So the dependent variable, i.e. the outcome, is quit smoking for a year, right? Yes. And it's a yes or no question, so it's appropriate for BLR. Our independent variable is attending the intervention, yes or no, right? So that's going to predict quitting smoking. And then we have some covariate variables, education level, income level, gender, that we think, based on our thorough review of the research, might impact quitting smoking. So we want to control for those factors as we observe the relationship between the independent variable, the intervention, and the outcome, quitting smoking. So again, a picture's worth 1,000 words, right? So we put our study map into a diagram, right? So on the left, we have our predictor variables, right? Our three covariates, an independent variable. And on the right, we have our dependent variable, quitting smoking after 1 year, right? Now, don't forget, we are not only looking at the direct effects, such as the direct effect of the intervention on quitting smoking, we are also going to examine indirect effects in this webinar. So specifically, we're going to look at the indirect effect of income moderating the relationship between attending the intervention and quitting smoking. Right? So there's all sorts of reasons to think income might impact quitting smoking. Right? So if you attend the intervention and you can't really afford the cigarettes, right? That might lead you to quit smoking faster. So we'll look at the moderating effect of income. Now, this will blow your mind from a statistical point of view. Step 3, the checks of data integrity. Specifically, we're going to be looking at the test assumption. So we have our 4 areas here of data integrity where data must be checked. Statistical power, missing data, measurement tools. But today we're focusing on test assumptions. And we're focusing on test assumptions because this illustrates, well, what a bargain BLR is to do, because you get the odds ratios and great findings, and the number of test assumptions is radically less than some other methods. Right? So specifically, recall the test assumptions addressed in a study are often based on the final multivariate model, which is often a regression model. So 2 of the most common multivariate models in cross-sectional analysis, right? So that's where the dependent variable is measured once, right? Is cross-sectional. If it's measured twice, it could be pre-post. If it's measured 3 times, it might be longitudinal, but measured once, cross-sectional. So how's that looked at? Often by either multiple linear regression, when we have a continuous outcome or dependent variable, and then binary logistic regression when we have a dichotomous outcome or dependent variable. Now here we go. So the test assumptions for a multiple linear regression, right, used for a continuous dependent variable. For example, if we were looking at number of cigarettes smoked daily, right, 1, 2, 3, 4, 5, it's continuous. As it rises, it shows more cigarettes. And so the test assumptions for a multiple linear regression, right, include normality, homoscedasticity, multicollinearity, linearity, the influence of outliers, right? It's a long list. Right? So if we take a closer look, right? So now remember, we're just talking about testing for these things. So if a test assumption is violated, that's a whole nother can of worms you have to open, right? So just testing for them is a lot of work. And then if there's troubles, that's a lot of work on top of a lot of work, right? So normality, right? So you have to test our normality, right? So the 0 is our mean, and the -4 through +4 are the standard deviations. So we have to test, of course, is the distribution of the continuous variables approximately normal, right? The percentages of the participants fall in between 1 standard deviation, 2 standard deviations, and so on. So we're just doing a for instance. We're going to go through them rather quickly. And then multicollinearity, right? So are 2 or more predictor variables in multiple regression highly correlated, right? So that can distort the findings in a regression model. So if we have something like number of years at work and age, those 2 are often correlated highly because as you get older, right, as you're working at a job and the years go by 1, 2, 3, your age is also increasing 1, 2, 3. So that could have detrimental effects on the findings. Right, linearity. So, right in the name, multiple linear regression, we have to make sure a continuous independent variable has a linear relationship with a continuous dependent variable. So recall that to the far left, we see a positive linear relationship, right? As x increases, y increases. In the center, we have a negative relation, where as y increases, x decreases. And then no linearity at all, right? So those must be checked for in multiple linear regression. Homoscedasticity, which is a task just to say, right? And never mind do, right? So you have to look at the homogeneity of the variance. Are all the residuals equally spread out, right? So we produce an image in our regression to check if that's so. Now our outlier scores. So outlier scores present a real threat to the multiple linear regression because just 1 or 2 outliers can totally change the findings, right? So those are those very high scores or very low scores in the distribution, maybe 3 standard deviations above or below the mean, right? Now, keep in mind, it's the undue influence of the outlier, right? That can like mess up our findings. So that's what we need to check for. So often, if we find some outliers, what do? We might repeat the multiple linear regression with a version of the variable with and without the outlier. Now, here's my point. This is the point of all this. The test assumption that we need to check for with binary logistic regression is essentially multicollinearity, right? So A, B, D, E, and F, we don't need to pay attention to, at the same level anyway. But multicollinearity is the main check for our regression model. Now that's what I'm talking about, right? So we're getting our odds ratio, which is perhaps the greatest effect size, right, we could end up with. And in terms of checks of test assumptions, we have a very reduced list just of multicollinearity. So as I said, that's the main check. Some people like to suggest that if you have a continuous variable as a predictor, you might want to check if it's normally distributed, because it might lead to more stable findings. So it's more of a suggestion, right? So we may use a t-test, for example, right? And that would be another instance where we would like to look at if there's a normal distribution and undue influence of outliers, because a t-test is a parametric test that might be susceptible to that. So although in a BLR study, right, our main check might be multicollinearity because that's the final multivariate model, but at the bivariate level, even if we don't report it in the paper, we might want to check, if the t-test assumptions are met, just for the integrity of the data. Okay, so now let's talk about actual application, right? So the first thing we always want to do is get to know our variables, right, in the analysis. So that's step 4, the univariate analysis, right? Uni meaning one, var meaning variable, right? So the analysis of one variable. So that's where we do our frequencies and we get to know the personal characteristics of each variable apart from the others. It's also called descriptive analysis because we're describing the variables. All right, so here we have our good old univariate test case, right? So what does it tell us? That the variables on the left, be they categorical or continuous, the univariate test to use is the frequencies. Right? And specifically, when it's categorical, we're presenting our number and percentages within each category. And when it's continuous, we're presenting the mean, the standard deviation, the minimum, maximum scores, etc. So, univariate analysis in SPSS. So we have the list of how to do it here, but we will actually go into SPSS and perform it just for good form. So here we are in our very small SPSS database used for our sample study. Right, just a little illustration. So to run our frequencies, of course, we go to Analyze, Descriptive Statistics, Frequencies. Then we put over everything. Right, so gender. Then if I click the top one, then hold down the Shift button, I can highlight them all at once, bring them all over. All right. Then I go to Statistics. We want the mean with the standard deviation, minimum and maximum, and skewness and kurtosis to see if it's a normally distributed variable. Continue. Then we have charts, and we would like to see the histogram with a normal curve. Continue. Then we could either paste it and save the syntax or click OK. I'll click OK. Okay, so here are the findings, but they are also in the slides, so let's look at them there. Okay, so here's where we left off. Okay, and here are our findings that were on the output. Okay, so the first one is income level. So like we said, sometimes it's nice to know if it's normally distributed and if there are outlier scores, even if it's not a hard assumption on BLR. So what do we have here? It's measured in thousands, so the mean is 33,170. Okay, so with the minimum maximum, 10,000 to 49,000, and the standard deviation is 8,870. So if we wanted to know if it's approximately normally distributed, we might look at first the outliers. So if the outlier is 3 standard deviations, that is 3 times 1 standard deviation of 8.87, which is 26.61. So that anything above the mean, so we take the mean and we add it and subtract it from 26.61, then we know if there are outliers. So the mean of 33.17 plus 26.61 is 59.78. So an outlier at the high end would be equal or greater than 59.78. And our maximum is 49, so it's below that, so there's no outliers above. And if we minus 26.61 from 33.17, we get 6.65. So a low outlier, an extremely low score, would be equal or less than 6.65. And the lowest value we have, seeing the min-max there, is 10. So there's no outlier scores to worry about their undue influence on the findings. So we're safe there. And if we want to know if the distribution is approximately normal, we could use the old computation where we say, is the skew 2 times, or you might use 3 times, but let's use 2 times, is the skew 2 times the standard error of the skew, right? And if it's not much greater than 2 or 3, then we could say it's approximately normally distributed in the center, right? The peak. That's what the skew refers to. So that's why we took our skewness and kurtosis. Those values are given. So if we divide the skew by the standard error of the skew, we get 2.38. So it's a ratio of 2.38. So the skew is a little bigger than 2 times the standard error, but not that much. Now the kurtosis is actually smaller than the standard error of the kurtosis. So the kurtosis refers to the dispersion of the scores, right, out into the tails and in the center. So we see if we divide the kurtosis by the standard error, because the kurtosis is smaller than the standard error, we get a 0.06, right? So in end, we have a 0.38, which is not that bad, and a 0.06, which is negative, which means it's less than. So it's approximately normally distributed. So if we look at our categorical variables, right, easy to put. So we have our education level. We see it's about almost half graduate school, right, in terms of education level, and almost a little more than a quarter high school and quarter college. Right, so our intervention group, so it's a little less than half, 48 in our intervention group. Right, gender, it's getting close to 2/3 female, and quit smoking. So just about half the people quit smoking. Will these be the same half of the people that are in the intervention? We're going to find out. All right, so 43 quit, 57 did not. So here's where we start our inferential analysis, our bivariate analysis. Now, often the goal of bivariate analysis, of course, is to determine which predictors, independent variables and covariate variables, have a significant relationship to the outcome, to the dependent variable. And if they have a significant relationship, we put them in the regression model in the next phase of data analysis in step 6, right? So we have our bivariate, bi meaning two, var meaning variable, so presenting an analysis between two variables. Again, we're using bivariate analysis to identify significant one-on-one relationships between the covariate variables and independent variable with the dependent variable to select predictors for step 6 multivariate analysis. So we are going to consider 2 ways to conduct and report bivariate analysis in our BLR study. The first is, you could call it the more traditional way, where we use the independent samples t-test and chi-square. And then second, the one I recommend is the single predictor logistic regression. Okay, so we have our old bivariate test case. This is for the first way, when we do the chi-square and the t-test. Okay, so which test do we need for our analysis? We just plug in our variables. So we have 3 categorical predictors being compared with our categorical outcome, quit smoking, in which we'll use the chi-square. Then we have 1 continuous predictor, income, with our categorical outcome with 2 categories, quit smoking, where we'll use the t-test. Now the other way we could do it is use single predictor logistic regression. Right? So this uses the binary logistic regression with categorical and continuous variables in the same manner. So we don't have to actually specify and use a different test. Now, this actually makes everything pretty cool because you can actually use the same tests essentially in bivariate analysis and multivariate analysis, that being the BLR, and that makes them comparable. So we'll discuss this later, but essentially you can see the effect size, the odds ratio predicting effect size at the bivariate level when it's just a one-on-one relationship. And then in the full context of the model, you can see how the odds ratios change when they all affect the outcome together. This is tremendously interesting, but let's get to it. Okay, so our goal in our bivariate analysis, right, is we want to determine significant relationships. So is gender related to quitting smoking at a statistically significant level? Is education related to quitting smoking, right, at a significant level? Annual income, quitting smoking, and is attending the intervention associated with a higher rate of quitting smoking after 1 year? That being our independent variable, our variable of interest. The other covariates we think will have an impact on quitting smoking, so we want to control for their effect, but they are not the variables of interest. Okay, the bivariate test keys. So, as we said before, we had variable A, continuous variable income, and variable B, a categorical variable with two categories, quitting smoking, yes, no. So we're going to test that relationship with an independent samples t-test. So what we're looking at is, do significant differences exist by mean scores, right, of the continuous variable, income, within the two categories of the categorical variable, quitting smoking, yes, no. Okay, so for our study, does the mean level of income differ significantly among people that quit and did not quit smoking? So here are instructions in SPSS. And so we can actually go right to SPSS to try that out. So analyze, compare means, and then independent samples t-test. So we take our grouping variable, which is actually group, right? No, just kidding. It's actually our outcome, quitting smoking. So here we go, quit smoking. Now, define groups. 1 means yes, they quit smoking, and 0 means no. So they're coded as 1 and 0, so we put 1 and 0 there. Continue. And then in the test variable, we're going to put our continuous variable income. And that's that. So click OK. And there are our findings, but let's observe them from this vantage point. Okay. Here we go. So what do we want to look at? A lot of numbers, but these are our main message numbers. So in the center of the second box, the lower box, we see the significance, the two-tailed sig, is 0.000. So it's below 0.05, so we know it's a statistically significant difference. Now the question becomes, just what is this difference? Whose score is higher than who? So up top, we see for quitting smoking 1 year, yes, their mean is 37.09. Quitting smoking no is 30.21. So the people who quit smoking have a significantly higher level of personal annual income relative to the people that did not quit smoking. So therefore, right, if we go back to our study map here, we see that's a significant relationship. So they will be included in our final multivariate regression model. Now here we go. Now we have the trifecta of variables where we have 3 predictors being tested all together with a chi-square test. So 3 different chi-square tests looking at gender and quitting smoking, the second intervention in quitting smoking, and the third education in quitting smoking. And what is a chi-square answer? It's that we're testing to see if the proportions within the categories, quitting smoking, yes, no, differ significantly by categories within the other variables. And so the research question might be, does the proportion of people who quit smoking differ significantly by the study participants in the intervention or non-intervention group? So here are the directions to complete a chi-square in SPSS. But of course, we're going to ascribe to the old do, don't say. So we go back, analyze, descriptive statistics, cross tabs. Then we could put our dependent variable in the column, quitting smoking. Then, for example, we might put, let me see, study group just to, because that's the interesting one in there. Right, then under statistics, we click chi-square, continue. Then under the cells, under percentages, we click row, continue. And then we either paste it and save it, or click OK. And there we go. So let's go back. There we go. So here are the findings between quitting smoking and the study group. So which values are of greatest interest to us? There you go. If we look first at the second box, there's a line that reads Pearson chi-square of ASYMP sig two-sided. That's to tell you the level of statistical significance of the test, which is far below 0.05. It's 0.000. So there is a significant difference. And if we look at the column for quit smoking yes, right, and we look at the intervention line, we could see that we see that in the intervention group, right, in the total, there are 48 study participants, right, so that's accurate. And we see of them, there are 33 in the yes column, which is 66.8% of them. So of the people that attended the intervention, over 2/3, 68.8%, quit smoking after 1 year. Now, the non-intervention group, there's 52 in total, and in the yes column, there's 10. So only 19.2% of them were quit smoking after 1 year. So that tells us there's a significant difference where people in the intervention group are significantly more likely to quit smoking. Now, we don't have to repeat it in SPSS, but these are the findings for education level. And we look at our numbers. So the bottom square says, right, 0.007 for significance. So it's a statistically significant difference. And then in the percentages, we could clearly see where that difference is. Where college and graduate school, a little over half each quit smoking, right? So for college and graduate school, 53.6 and 52.3 respectively. But at the high school level, only 17.9% quit smoking after 1 year. Now we have gender. And if we look at our key numbers, we see the significance on the bottom is 0.43. So it's not a significant difference. So gender won't go into the regression model. And we can also see, in terms of the percentages in the yes column, they're very similar, i.e. there's no significant difference, right? 41 versus 44.3%. Right? So our goal is to answer which are significant. So we saw the gender's not, and the other three predictors are. So there we go. Now, when we do our single predictor logistic regression, right, we're probably going to come out with the same findings as the t-test and chi-squares, right, because it's both based on differences. So first, before we do it, let's illustrate it in SPSS. So we go to our analyze and our regression. There we go. Binary logistic, right? So the smoking. So we put the quit smoking in the dependent, right? Because that's our outcome. Now, gender is the one we don't want, right? So what we want to put in there is, for example, study group. Okay. Now, we always want to click categorical and get our, this is categorical, options, and check our CI for exponent B. Exponent B is the odds ratio. So it's the confidence interval, 95% for the odds ratio. Continue, and OK. Then we can observe the numbers from here. OK. So it's just a single predictor logistic regression. So all we have is one only single predictor in the output. So the first thing we're looking at is the significance. So study group is significantly related to quitting smoking. Okay, right? We saw that too with our other bivariate test, right? We know it's positive, right? So study group goes from 0 no or 0 control to 1 intervention, right? And then quitting smoking goes from 0 no to 1 yes. So it's a positive relationship because there's no minus in front of the beta, right? If it was negative, it would be minus 2.22. So it's positive. So that means as we go from 0 to 1, from control to intervention, we're significantly moving also from 0 to 1, not smoking to quitting, not quitting smoking to quitting smoking. So you have to know the coding to interpret it. So it's a positive. So that means that the intervention group is more likely to be quitting smoking, but how much more? So then we look at the odds ratio effect size, 9.24. So we could say that those in the intervention group are almost 10 times more likely to have quit smoking after a year relative to the control, right? And then we look at our confidence interval. You can see we could round it to 3.7 and 23.2. So that's kind of a wide range, right? Because 23 is a huge effect and a 3 is a smaller effect, right? So the smaller the confidence interval, the more stable the findings. This is a little wide, but it's not too bad. Sometimes you'll see them from 4 to 100. So this is yeah, on the more moderate side. So here's something that just looks pretty, okay? This is the table for the single predictor binary logistic regression. Now, if we did our chi-squares and we did our t-tests, we need two different tables, right? So there's no homogeneity in there. So we'd have a t-test table, we'd have a chi-square table, then we'd have a binary logistic regression table for the full model. But this way, they all sort of work in tandem because here we have the exact same values that we're going to have in the full multiple logistic regression. We can see how they change all together, but we can also observe what they look like all by themselves. Now you'll notice one of the things we did in the table here is we put the cross tabulation. Right? So on the left side of the table, we have the actual numbers and percentages of the intervention and control group that quit and didn't quit. Right? So that's the information from the chi-square. Very interesting. So that's where we have our yes column, where the intervention 68.8% quit, right? That first column there. And the control only 19.2% quit. So we have all that information. And then on the right side, we have the actual results of the single predictor binary logistic regression. The most exciting of those is the p-value, right? So we know it's significant, the difference is significant, 0.001, and the odds ratio, almost 10 times more likely. So you have a tremendous amount of information in this little table, and then it's also comparable to our full model. It's very exciting. So we'll also send a sample writing, illustrating all this. It'll also be more exciting when we have our full BLR model to compare with this bivariate level, which will be next session. Right, so the results of what we have here, we have our two covariate variables and the independent variable having a significant relationship with the dependent variable. Now you can't tell which is the strongest. Some odds ratios might be bigger or smaller than the others, right? But that doesn't mean it's the strongest because, like we said, when you put them in the model together, some odds ratios might increase and some might decrease. So you can't tell just from the one-on-one odds ratio. You need the full context of the model. Right? So, which will be in step 6. The multivariate analysis, the BLR, will tell us in the full context of the model which is the strongest predictor of the outcome. And of course, if it's an intervention, we would hope that would be the strongest predictor. Right, so in session 2, we're going to be going over the multivariate analysis to reveal those direct effects we just mentioned. And also, we'll be looking at the BLR interaction effects to reveal the significant indirect effects. Okay, thank you for watching, and we'll talk to you next session.